Well, thanks for the introduction. Thanks for the introduction, and thanks for having me. It's really a pleasure to speak in the seminar. I attended last week, and last week was really interesting, and I looked at some of the speakers coming up, and it looks really interesting. So I'm really pleased to talk in this seminar. So yes, I'm going to talk about arithmeticity of quaternionic modular forms on G2, and of course, I'm going to explain, what I mean by arithmeticity and what are quaternionic modular forms, and maybe a little bit about what is G2. So let me just start with arithmeticity of classical modular forms. So in short, what I mean by arithmeticity of classical modular forms, so in a sentence, is just that if you look at the classical holomorphic modular forms, they have a Fourier expansion, and the Fourier coefficients are frequently algebraic numbers, or even rational numbers, or even integers. And so that's roughly what I mean by arithmeticity. So let me just review very briefly. So let me denote by H the complex upper half plane, and suppose gamma inside of SL2Z is a congruent subgroup. So a classical holomorphic modular form of weight L, so L will be some non-negative integer, is, as we know, a function f from the upper half plane to the complex numbers that satisfies the following three properties. So it has a equivariance condition for all elements in the subgroup capital gamma in terms of the power L. It has moderate growth in some sense. So more precisely, if imaginary part of Z goes to 0 or goes to infinity, then f grows polynomially in the imaginary part of Z, and it's holomorphic, that of course being a crucial condition. So suppose for simplicity that the congruent subgroup gamma is all of SL2Z, then you have a simple Fourier expansion. F of Z is the sum AF of n, e to the 2 pi n Z, or over non-negative integers n, and if the zeroth coefficient is 0, then f is a cusp form. And as we know, modular forms you can equivalently think of them as sections of holomorphic line bundles on the space H mod SL2Z. So here, I guess I switched notation here from math frac H to math cal H, but this H1 is just supposed to be the complex upper half plane. So what do I mean by algebraicity of Fourier expansions? So if I take a subring R of the complex numbers, I can denote by ML gamma of R the modular forms for SL2 of weight L, level gamma, and all of whose Fourier coefficients are in the subring R of the complex numbers. And so here's a weak form of the algebraicity of the Fourier expansions. One can certainly prove much stronger results, but for my purposes, I'll just state this weak form. So I'd let Q cyclotomic denote the cyclotomic extension of Q. So Q join all the nth roots of unity. And then this theorem, I think it goes back to Shimura. Someone can correct me if I'm wrong. That says that the modular forms of weight L and level gamma, they have a cyclotomic structure. So if I look at all the modular forms whose Fourier coefficients are in Q cyclotomic, then they span all of the modular forms over the complex numbers. So I have this tensor product relation. Okay, so in other words, I have a basis of the weight L modular forms, all of whose Fourier coefficients are in the cyclotomic extension. So I like to think of this this classic result as sort of, on the one hand, being saying something about the fact that modular forms are related to algebraic geometry. So one way to think about that is that I could take the graded ring of modular forms of weight L. So I fix gamma, I fix my congruent subgroup, and I take the graded ring of modular forms. So I let L vary from 0 to infinity. And I just look at the modular forms with Fourier coefficients in the cyclotomic extension of Q. Then I have this graded ring, so I can take its proj, and I get a projective curve now defined over the cyclotomic extension of Q. And this curve has the property that if I take its complex points, I get a compactification of H mod gamma. Okay, so we can sort of see that this arithmeticity has maybe some relationship to algebraic geometry. And and this is just I'm just stating this result for SL2, but one could state equivalent or not equivalent. One could say that analogous results if I replace SL2 by any Shimura variety, any group that has a Shimura variety, and then talk about the holomorphic modular forms. So what I want to do is, and the point of this talk is to give an analog of this theorem 1 to where SL2 is replaced by G2. And one thing that will come up in the proof, even though I haven't stated what the result is yet, one thing that will come up in the proof is the use of theta functions. So I just want to review theta functions, classical theta function for SL2 before I move on past SL2. Okay, so here we go. Suppose V is a finite dimensional real vector space with a positive definite inner product on it. And let me suppose I have a lattice L inside of V that's integral for my inner product. So technically speaking, I'll suppose that the inner product of a lattice vector X with itself is an integer. And if I take two vectors, X and Y, not necessarily the same, then at least I get a half integer. So in this setup, I can define an associated theta function where I sum up over all vectors in the lattice, e to the 2 pi I, V paired with itself times the complex parameter Z, which sits in the upper half plane. So I sum this up, and then it turns out it's a consequence of Poisson summation that this is a modular form for some congruent subgroup gamma of weight dimension of V over 2. Okay, so I get, at least if the dimension of V is even, I get a classical holomorphic modular form, and if the dimension of V is odd, then, well, you get a half integral weight modular form. It's a little more complicated. So that's classical theta functions. And I also want to describe harmonic theta functions. This is a very classical topic because eventually I'm going to get to producing some analogs of these harmonic theta functions where SL2 is replaced by G2. Okay, so I let V, L, and the inner product be as above. So V is a real vector space. The inner product is positive definite. L is a lattice in V, and the inner product has integrality properties on the lattice. Now, I take some vector W in V tensor C that's isotropic. So of course I can't find such a W in V, a non-zero W in V, because the inner product is positive definite. But once I complexify, I can certainly find isotropic vectors. So isotropic just means that W paired with itself is 0. So once I have such an isotropic vector, I can consider all polynomials on V with range or with codomain the complex numbers, defined as I input some vector V, and then the output is I take the inner product with W and I raise it to the nth power. So n is some fixed integer, non-negative integer. So if I look at all the polynomials that I get in this way, this spanned by these specific polynomials with isotropic vectors, these sorts of polynomials are called harmonic. And it gives me an irreducible finite dimensional representation of SOV. SOV acts on this set of polynomials just by changing variables, and this is a particular representation of complex representation of SOV. So now let's say I have such a harmonic polynomial P. I can make a new theta function where instead of summing over 1 times this exponential over lattice vectors, I sum over P of V times this exponential over lattice vectors. So this turns out to again be a modular form. Its weight is dimension of V over 2 plus n. And it turns out, incredibly, that if n is positive, then I get a cusp form. So this is a great way of creating cusp forms on SL2. Okay, oh, and I should have said at the beginning, if anyone has any questions, if anything I say is unclear, please, of course, feel free to ask. So let me give a nice concrete example of harmonic theta function. So I'm particularly fond of this example. So I define S to be this particular 8 by 8 matrix. And it turns out this S doesn't come out of nowhere. This is the unique, up to change of basis, this is the unique even unimodular lattice of rank 8. It's the smallest non-trivial one. And so I let V be R8, L be Z to the 8, and I define an inner product on V on R to the 8 using this matrix S as the Gram matrix. So in other words, X paired with Y is 1/2 X transpose SY, where I'm thinking of X and Y as column vectors. So S is positive definite. So this gives me an inner product, and this pairing is integral on my lattice. Okay, and I can make a harmonic polynomial just by taking E1 plus I E2, where E1 and E2 are the first and second standard basis vectors of V. So E1 plus I E2 is isotropic. And so I get a harmonic polynomial by pairing V with E1 plus I E2 and raising it to the 8th power. And then I get an associated theta function by summing up this polynomial P of V times e to the 2 pi I V paired with V times the complex number Z. And so if you believe everything I said, I should be obtaining a cusp form of weight 8 over 2 plus 8. So dimension of V is 8, and the n here is 8. So 8 over 2 plus 8 is 12. So I should be obtaining a cusp-form of weight 12. And indeed, you get 1920 times Ramanujan delta function. So this is a nice way of constructing Ramanujan delta function, in my opinion. Okay. So that was my recap from classical modular forms. And I'd like to define modular forms in a bit more general, in a bit of a more general way for semi-simple Lie groups. Okay. So I suppose I have a semi-simple Lie group G, which technically speaking, I really think of it as the real points of some semi-simple algebraic Q group. And suppose I have an arithmetic subgroup gamma inside of G, which again, I really think of as coming from the rational structure of some algebraic group over Q. So technically speaking, it would be, I take the rational points of an algebraic group and I intersect some compact open subgroup of the finite adelic points of G. But in any case, I have some arithmetic subgroup gamma of G, and I have a smooth function phi on G. So in the setup, I'll say that phi is a cuspidal modular form if the following conditions are satisfied. So this is a reasonable definition. It's not exactly the standard one, but it's a reasonable one. So one is that I suppose that phi is left invariant by gamma for all little gamma in capital gamma. I suppose that it satisfies a simple linear differential equation, d phi equals 0, first order even. And so technically speaking, so I'm not going to be precise in this talk. At no place in this talk will I be precise about what exact differential equation I want to require. But the differential operator D will come from the right regular action of G on G mod gamma. So Gx on the right of G mod gamma, I can differentiate that to get a Lie algebra representation of the Lie algebra of G on smooth functions on G mod gamma. And when I say that I've got a differential equation, it's coming from that Lie algebra action. But in any case, I just have some first order simple linear differential equation. And then finally, I'll assume that phi is bounded. So this boundedness is supposed to be the cuspidal part of this definition, whereas the parts 1 and 2 are supposed to be the modular form part of this definition. So like I said, it's not exactly the standard way of phrasing things, but it's a reasonable way to proceed. So I also want to discuss weights of modular form. So this is a cuspidal modular form. What is its weight supposed to be? So its weight is supposed to be a representation of the maximal compact subgroup K of G. So again, G is a semi-simple Lie group, and I'm going to let K, capital K, denote a fixed maximal compact subgroup of G. And now I assume that I have some finite dimensional complex representation of K. Okay, and I'll call that representation rho, and it'll act on the vector space V. And now I assume phi is a modular form of level gamma for the group G that's valued in the finite dimensional vector space V. So phi is a function from G to V that satisfies these conditions. It's symmetric, it satisfies a differential equation, and it's bounded. And then in this setup, I'll say that phi has weight rho for the representation rho if it's rho equivariant on the right. So phi of GK is rho of K inverse phi of G for all K, little k in the subgroup capital K. Okay, so this is a sort of a group theoretic way of proceeding, defining modular forms and talking about their weights. You could also proceed somewhat geometrically. So just another way of rephrasing exactly what I just said is to look at the locally symmetric space, G mod gamma mod K. So I mod it by K on the right and by gamma on the left. And if you have a representation rho of K, then I can use that to make a vector bundle over this locally symmetric space. So technically speaking, I just write G mod gamma times V, and I identify K acting on the right of G mod gamma with K inverse acting on the left of V, or with K acting on the left of V. And this gives me a vector bundle, V over Y, where Y is the locally symmetric space. And the weight condition on phi is just exactly that it defines a section of this vector bundle over the locally symmetric space. Okay. So one last slide about classical modular forms. So this slide just says that classical modular forms can be understood in this group theoretic framework that I've written on this slide here. Okay, so I think probably lots of people are familiar with this, but I'll just review it in case people are not, or in any case, in case one's forgotten, because it's easy to forget these sorts of things. So, so to be precise, suppose I have a holomorphic modular form F defined on the complex upper half plane, and it's of weight L and level gamma. If I let J denote the usual factor of automorphy, J of GZ is CZ plus D, if G is ABCD, then I can, out of my holomorphic modular form F, I can obtain a function phi sub F on SL2R valued in the complex numbers via phi sub F of G is, well, I let G act on I in the upper half plane. I put the quantity G acting on I into F, and then I twist by this factor of automorphy, J of Gi to the minus L, where L again was the weight. Okay, and then it turns out if you do this, then phi sub F is, of course, a smooth function. It's left invariant under gamma instead of transferring under this factor of automorphy. It has moderate growth. It has a right equivariance under the maximal complex subgroup SO2. So SO2 here is the maximal complex subgroup of SL2R. And you can write all the elements in this compact group SO2 as sort of as rotations. So k sub theta. And you have an equivariance condition, phi f of g k sub theta is phi f of g times this exponential. And then finally, corresponding to the fact that f was holomorphic, it satisfies the Cauchy-Riemann equations. This function phi sub f, it turns out, satisfies a first order linear differential equation that comes from the Lie algebra action of SL2. So this is a way of starting with the classical modular form, holomorphic modular form, and getting a group theoretical one, and you can go backwards. If you have a function phi that satisfies these conditions 1, 2, 3, you can obtain a function f sub phi on the upper half plane valued in the complex numbers, just sort of reversing this construction. Okay. Okay, so that was sort of my preliminaries. I think I'm doing great on time. Maybe I'm going a little too fast. We'll see how much time I have at the end. So, so with this sort of preliminaries, I wanted to say, what I mean concretely about G2 and modular forms on G2. Okay, so let me just, I think most people are probably not familiar with what the group G2 looks like. So I have a couple slides on G2. So first of all, G2 is a simple algebraic group over the rational numbers. And I'll tell you how to define it, or roughly speaking, how you can define it. So I start with the group SL3, and I'm going to build G2 sort of out of SL3. Okay, so first I build the Lie algebra of G2. So I let SL3, mathfrak SL3, be the Lie algebra of the group SL3, which is the 3x3 matrices with trace 0. So you could be working over the rational numbers here, over the real numbers, whatever. I guess I've sort of phrased things in terms of working over the real numbers, but you could work over the rational numbers. I let V sub 3 denote the standard three-dimensional representation of SL3 of just matrices acting on column vectors. And I let V3 check be the dual representation. So just as vector spaces, I define the vector space G2 to be the direct sum of these three vector spaces. So SL3 plus V3 check. So this is dimension 14. So SL3 has dimension 8. It's a 3x3 matrix of chase 0, and then V3 and the V3 check each have dimension 3. So you can define a Lie bracket on this vector space that turns G2 into a Lie algebra in such a way that SL3 is a subalgebra. So I know how to define a bracket from SL3. It's just xy minus yx, if x and y are 3x3 matrices with trace 0. And you can extend that bracket. What I'm saying is you can extend that bracket to this vector space G2. And so, for example, if M is in SL3 and V is a column vector in V3, then the bracket of M with V is just M times V. where on the right, I mean M is a matrix and V is a column vector, and I'm just doing matrix multiplication. So M times V again sits in V3, and that's what the bracket of M with V is. Okay, and then you could do a similar thing for the other brackets that are slightly more complicated. So this is how you can construct the Lie algebra of G2. And then how do you define the group G2? Well, you can always, whenever you have a Lie algebra, a semi-simple Lie algebra, you can get a semi-simple group just by taking the linear maps from the Lie algebra to itself that preserve the bracket. So I let the group G2 be the set of G and GL14, the general linear group of this 14-dimensional vector space that preserve the bracket. So GX bracketed with GY is G acting on X bracketed with Y for all X and Y in the Lie algebra G2. Okay, great. So this defines the group G2, and I want an arithmetic subgroup, and one way of defining an arithmetic subgroup of G2 is as follows, and this is a perfectly good choice. So it turns out that this group G2 has a 7-dimensional irreducible representation. So it's a map rho from G2 into GL7, and I can just take the 7x7 matrices with integer entries, and I let G2 of Z be the G in my real Lie group G sub 2, G2, such that when I push them over to GL7, I get an integer matrix. Okay, so this gives me a nice subgroup of G2, and it has the property that it's infinite. And on the one hand, on the other hand, if I take G2 and I mod out by this subgroup, I get something that's non-compact, but at least has finite volume. Okay, so now I've defined the Lie algebra of G2, the group G2, an arithmetic subgroup, G2 of Z. And the last sort of piece of data that I want is, to make precise, is a maximum compact subgroup of the real group G2 and some representations of this maximum compact subgroup, so I can talk about weights of modular forms on G2. Okay, so a maximum compact subgroup, it turns out, can be identified with the compact group SO4, which SO4 has an exceptional isomorphism with 2 copies of SU2 modded out by a diagonally embedded plus or minus 1. Okay, and so you can see, what are some complex representations of this maximum compact subgroup, finite dimensional representations? Well, I can take one particular set of representations, which will be relevant for what I want to discuss, is the following. I let the second SU2 factor act trivially, and I let the first SU2 factor act on its irreducible 2L plus 1 dimensional representation. So in other words, I take the standard representation of SU2 on C2, I take its 2L symmetric power, and so that's, of course, dimension 2L plus 1, and this gives me a representation of SO4 or K, okay, and I've called this representation V sub L. Okay, so V sub L is an irreducible, complex 2L plus 1 dimensional representation of the maximum compact subgroup K.
Quick question. How does the maximal compact act? How do you view it as a subgroup of G2 using your definition above?
Yeah, so the best, I think the easiest thing to do is you go back to the Lie algebra. There's a couple things you could do. So one is you go back to the Lie algebra and you define a Cartan involution on the Lie algebra. So there's an involution on the Lie algebra that has certain positive definiteness properties with respect to the killing form, and you let the maximum compact subgroup to be all the elements of G2 which commute with this involution. That's one way to do it. Another way to do it is, if you believe what I've said about the existence of this map representation from G2 into GL7, you can just take SO7, the compact group SO7 inside of GL7, and you just let K be all the elements of G2 that map into SO7. So the inverse image of SO7 and G2. That's another way of defining a maximal compact subgroup. Yeah, thanks for the question.
Okay, thanks a lot.
Maybe one more question. This 7-dimensional representation, rho, can it be described in terms of the Lie algebra that you wrote in the previous slide, which has dimension 14, or it has nothing to do with the Lie algebra?
It's not so easy to, so it's easier to go the other way. If you give yourself the 7-dimensional representation, then you can find the Lie algebra inside the exterior square of the 7-dimensional representation. So you see the 7-dimensional representation, the exterior square is 21-dimensional. It turns out as a representation of G2, it breaks up into a 14-dimensional piece and the 7-dimensional representation again. And so then that 14-dimensional piece is the Lie algebra.
Okay, thank you.
Mm-hmm. Okay, so we have all the data now to discuss modular forms on G2. I've said the group, the arithmetic subgroup, and represent the K maximum complex subgroup, and representations of K, specific ones that I'm interested in. So here's a definition of modular forms on G2, roughly, which is just a repeat, basically, of what I had earlier in the talk for general modular forms on a general semi-simple Lie group. Okay, so I let gamma inside of G2 of Z, but define an index subgroup, and L a positive integer. I exclude L equals 0. And here's my definition of cuspidal modular forms. So cuspidal modular form of level gamma and weight L is a smooth function from G2 to the 2L plus 1 dimensional vector space V sub L that satisfies the following properties. So it's gamma invariant, it's K equivariant for the map rho. So K inverse on the right of equation 2 here, K inverse is acting via the map rho, the representation of K on VL. It satisfies a particular special linear differential equation, DL of phi is identically 0, and it's bounded. And again, so the modular form part of this definition is 1, 2, and 3, and the cuspidal part is the boundedness, part 4. So everything here is sort of simple, except for what's the right differential equation to take in order to get something interesting. And so that part essentially goes back to work of Gross and Pollack and Gangros and Savin. Okay, so this definition is a paraphrase of something that they wrote down.
One more question. Does this imply that the form would be harmonic in the usual sense?
It does.
I see.
At least if the weight is sufficiently large.
Okay. And so this operator is, I can think of it as somehow its square is somehow related to a Laplacian.
It's okay. So what's true is that it's a much stronger condition so it's true that if you satisfy this equation DL equals 0, you're necessarily an eigenfunction for the Casimir. So one can prove that. And so in that sense, satisfying this equation implies you're an eigenfunction for the Laplacian, but yeah, this is a stronger condition.
Thanks.
So it's a ring of invariant differential operators. Is it rank 2?
So it's not so I think what you're referring to is if I take like the center of the universal enveloping algebra,
right?
And consider, so usually when people define automorphic functions, they say, I want it to be an eigenfunction for the center of the universal enveloping algebra of my Lie algebra. But the center it's going to have elements like of degree 2 and degree 3. I don't know about degree 3, but at least of degree 2 and higher, but it won't have any element of degree 1. So other than, and so like sort of the smallest quote unquote thing you could take from the center of the universal enveloping algebra, I believe is going to be the Casimir, the smallest non-trivial thing, which is degree 2, but this is just a degree 1 operator. So I would think of it as being an analog with the Cauchy-Riemann equations. You just have a first order equation, which gives you a lot of rigidity.
So can you think of this first order as like a GCD of the second and third order? Like the second, third order, you put some other.
I don't know how to do that. Yeah, I've never.
But you say that Casimir, the second order is the composition of this first order and some other first order.
I can't remember. I worked it out maybe a year ago. I can't remember exactly how the proof goes, but I remember proving that if you satisfy this equation, then you an eigenfunction for the Casimir. But I can't remember. I think you're right. Like it's something that's like this and then something else, but I can't remember if that was actually what the proof was. Like it doesn't, I don't know if the Casimir actually factors as like,
oh, okay.
Yeah, square, something, yeah.
Okay, thanks.
But yeah, no, this is, on the one hand, it's a crucial part of the definition because it gives the functions all their rigidity. But on the other hand, maybe I don't want to spend a few slides making it precise, but of course I'm happy to discuss it later or something. It's just a little technical. Okay. Okay, so with this definition, it turns out that these modular forms have a pretty robust sort of semi-classical Fourier expansion. So this is a theorem that I proved a few years ago, or maybe it's 5 or 6 years ago now, that says that these modular forms on G2, in the sense of this definition here, have a robust Fourier expansion. So to set up the theorem, I take a real binary cubic form f, so AU cubed plus B squared V plus ... And associated to this binary cubic, it turns out there's a completely explicit function W sub f defined on G2 that takes values in this vector space VL, this 2L plus 1-dimensional representation of K, that satisfies a couple of the conditions of being a modular form. Namely, it's K equivariant and it satisfies the differential equation. However, the WFs are not gamma invariant. Okay, so the WF just satisfies conditions 2 and 3 here. Then it turns out that if phi is a cuspidal modular form of level gamma and weight L, then you can expand more or less phi in terms of these functions WF. So phi of G is, roughly speaking, it's not exactly equal to, but it's roughly equal to a sum of these infinite linear combination of these functions WF, where you're summing over f that are integral binary cubic forms, A, B, C, D are integers, and the a phi of f's are complex numbers. So phi of G is an infinite linear combination of these WFs, and the a phi of f's are what I call the Fourier coefficients of phi. Okay, so the theorem, it goes back to work of Nolan Wallach and a little bit of Gangos and Savin. And so they had proved the existence of the Fourier coefficients without the completely explicit Fourier expansion. Okay, but anyway, one could just prove this expansion. And so you can think of the WFs as sort of analogs, if you will, of the exponential functions that appear in the Fourier expansion of classical modular forms. Okay, so any classical modular form can be written as an infinite linear combination of the exponential functions with complex number coefficients. And then we're just saying something analogous happens here on G2. Yeah, so this is the Fourier expansion, which I'm not going to, the proof is conceptually simple, but it's just a little, it's sort of a computation. And I won't get into this right now, but you have this expansion, and then you can ask, do these Fourier coefficients A phi of f, do they have any algebraicity properties, right? They're just sort of defined in this very transcendental way as like the complex numbers that appear in this expansion, this sort of purely transcendental expansion. Okay, but nevertheless, it turns out that the Fourier coefficients do have some algebraicity properties, and that's the main theorem that I want to discuss with everyone today. So,
sorry, can I ask, do both the cubic forms that appear, do you get forms both of positive and negative discriminant, or?
Oh yeah, great question. Only the ones with positive discriminant.
Okay, thanks.
Yeah, so in other words, if you take a binary cubic with negative discriminant, then the Fourier coefficients A phi of f are just identically 0. That's one way of thinking about this.
And this has to do with the moderate growth condition, I suppose. Like
that's exactly right.
I see. Thank you.
Mm-hmm. Okay. Okay. So here's the theorem. So for a subring R of the complex numbers, I let S sub L of gamma with coefficients in R be the cuspidal modular forms of weight L and level gamma, all of whose Fourier coefficients sit in the subring R of the complex numbers. And again, I denote Q cyclotomic to be the cyclotomic extension of Q. So here's the theorem. suppose L at least 6 is even. Then there's a basis of the space of cusp forms of weight L and level gamma, for which all of the Fourier coefficients of elements of the basis are in the cyclotomic extension of Q. So in other words, there's an arithmetic structure on the space of cuspidal modular forms of weight L, defined in terms of these Fourier coefficients. Okay, and so I just want to point out that this is in contrast to, on one hand, it's of course very similar to what we saw for classical modular forms, but on the other hand, there's a contrast which I want to bring up, which is that G2 does not have a Shumor variety. So in other words, G2 mod K, the maximum complex subgroup, does not have a G2 invariant complex structure. So there's not any algebraic geometry that one could use to help prove this theorem, at least in any obvious way. Okay. So now I want to discuss what the proof of the theorem. How does that go? So it starts with a theta lift. So the proof of this theorem is to basically find a way to write down all cusp forms of weight L and level gamma in such a way, in a concrete way, so that one can just inspect the Fourier expansion of these cusp forms and just see that they usually have Fourier coefficients in the cyclotomic extension of Q. So the proof of the theorem is pretty constructive. Okay, so how do you construct cuspidal modular forms on G2? Well, the trick is you can use a bigger group, in this case, E8. So there's a group which I've called E84. It's commonly called E84, which is of type E8. It's a real Lie group of type E8, non-compact, which has real rank 4. So that's what the 4 means. And there's a notion of modular forms on this group E8, and they similarly have weights. And there's a family of weight 4 modular forms, which I've called theta phi of G, on this group E84, which are defined by Wietekan. So they take values in the same representation, or the same 9-dimensional vector space V4. So recall VL was a 2L plus 1-dimensional vector space. So V4 is 9-dimensional, and these functions theta phi, they always take values, or they take values in V4, this 9-dimensional space. So now there's a compact group. Let me denote F4C, the compact group of type F4. And it turns out that my group G2 times this compact group of type F4 sits inside of E8. So now what I can more or less do is I can use the functions theta phi of G on E8 as kernel functions to lift functions on the compact group F4 to automorphic functions on G2. So to make that precise, here's one way of making that precise. And maybe this is a little too precise for a talk, but it just so you can see, roughly speaking, what's going on. So it turns out that this group F4C has an irreducible representation, which I've called U1, which is of dimension 273, just a particular irreducible representation. That has some highest weight. I can multiply that highest weight by M, and I denote by use of M the irreducible representation of F4C with that highest weight, M times that of U1. So now, if I take my modular form theta phi of G on E8, I can apply a bunch of differential operators to it, which I've written here D upper M of theta phi of G. So this is like an M, D upper M is an mth order differential operator. And I get an automorphic function on E8. So not a modular form in the sense that it doesn't satisfy a particular special first order linear differential equation, but it's still an automorphic function, perfectly reasonable automorphic function. And when I do this, I get something that's valued in the vector space V4 plus M tensor the dual of UM. So one thing you could do with this D upper M is, since it's valued in this representation V4 plus M tensor UM check, I can pair it with an element alpha in UM. So I take alpha to be in UM, and I kill off the UM check, and I get something valued in V4 plus M. So this is going to be my function on G2. So I take G and G2, I embed it inside of E8 like so. I differentiate this theta function M times to get an automorphic function on E8, I plug in G, and then I pair with my alpha and UM check, or excuse me, my alpha and UM, and I get a function on G2, which is valued in V4 plus M. Okay, and so it follows from work of Witek, Gan, and Gordon Savin and Huang Penzig Savin that this theta phi of alpha is in fact a cuspidal modular form on G2 of weight 4 plus M. So this is some way of creating cusforms on G2 from data on F4 and on E8 using the dual pair G2 times F4 and E8. Okay, so even though you can write down this theta phi of alpha, and it follows without much work from Gan Savin and Huang Penzig Savin that this is a cusform on G2 of some particular weight. Even though one can do that, it's not at all clear if you get something non-zero or what its Fourier expansion looks like. So so one of the main theorems is that you can in fact explicitly compute the Fourier expansion of this theta lift, theta phi of alpha. So the Fourier expansion can be calculated explicitly, in particular, if alpha sits in some lattice in UM, so I've just said alpha is rational, and the theta function, theta phi on E8 is rational in a certain sense, then the theta lift has Fourier coefficients in the cyclotomic extension. So the theorem itself that I actually prove is really an explicit Fourier expansion for this theta lift, but this is just a summary of that result that says that if you take the data to be rational in a certain way, then the theta lift has rational Fourier coefficients or cyclotomic Fourier coefficients. Okay. So the reason I discussed theta functions, classical theta functions, at the beginning of the talk is that this theorem 4 is supposed to be an analog of classical harmonic theta functions. So, so the explicit formula for these Fourier coefficients of the theta lift is completely analogous to the Fourier expansion of harmonic theta functions. So the Fourier coefficients are finite sums over some lattice, and they're related to the finite dimensional representation theory of the compact group F4. So just like when we saw in SO2, the Fourier coefficients of harmonic theta functions are finite sums over lattice and related to the finite dimensional representation of the compact group SO8. Here we have a different lattice and replacing SO8 by F4, a compact group of type F4, but you can still, it turns out that the formulas are completely analogous. Okay, so this gives you a way to create lots of cusforms on G2 of weight 4 plus M. And so the weight has to be at least 4. And also gives you a way to, when you do this process to create these cusforms, it gives you a way to control the Fourier expansions. Okay, we can say something pretty concrete or completely concrete about the Fourier coefficients. So in order to prove the algebraicity theorem, this theorem 3, it'll suffice to prove that all of the cusforms on G2 of weight 4 plus M can be arise from this process of theta lifting from F4. Okay, because again, I can control the Fourier expansion of everything that's a theta lift from F4. So if I can just prove that everything on G2 is a theta lift from F4, this compact group of type F4, then I'll win. So the second part of the proof of the algebraicity theorem is to indeed show that everything, every cusform on G2 that's a modular form comes from this compact group of type F4. So that's bullet point 1 here. So how does that work? So the first thing to observe, and it's quite easy, is that, I mean, it's not hard to prove, is that if the set of lifts from F4, so it gives me some subspace of the cusforms of weight 4 plus M on G2, and the subspace is Hecke stable. So that's just an observation one can make. And so I can take an eigenbasis, a Hecke eigenbasis for this subspace, and extend it to an eigenbasis for all of the cusforms. Okay, so I have this orthonormal basis, if you will, of eigenforms on G2. And I know that the theta lifts are spanned by some subset of this orthonormal eigenform basis. Okay, so in order to prove that everything is a lift from F4, I just have to prove that any given eigenform is not perpendicular to all of the theta phis. Okay, all of the theta phi alphas. Okay, so another way of writing that is that if I take some given eigenform phi in G2, on G2 of weight 4 plus m, then if I integrate first on the G2 side to give me an element of UM check, I need to know that this integral here is not zero. Okay, because if this integral is not zero, then I can pair with some element of UM to get a cusp form just to see that the eigenform phi is not perpendicular to theta phi of alpha. Okay, so this, by the way, this pairing inside the integral is just a pairing on v4 plus m. So phi of g is valued in v4 plus m, dm theta phi is valued in v4 plus m tensor um check, and I pair away the v4 plus m parts and integrate over g2 to get an element, just a vector in this um check. So I'd like to prove that if phi is an eigenform, this integral over g2 is not zero. So one way to show that this integral is non-zero is to provide a linear functional on um check, and to see that that linear functional, when I apply it to um check, is not zero. So the linear functional I'm going to apply is an integration over a compact group of type spin 8. So to be precise, inside of the group E84, I can embed two groups, a product of two groups, spin 4 times spin 8. So I've called D4S for split, S for split, this group spin 4, and D4C, C for compact, the compact group of type spin 8. Okay, so this, it turns out, embeds inside of E8, and the G2 sits inside of this split D4. So all in all, it suffices to prove that if phi is an eigenform, then if I take this theta function, theta phi, I differentiate it m times, and I plug in G paired G comma H, where G is in G2 and H is in this compact group of type D4, and I do this integral, then I get something non-zero. So why all this, why all these different groups and why this particular integral? So the reason is that you could say something finally about the integral of the theta function over this compact group of type D4. Okay, so the integral of this theta function, so you can change the order of integration. Instead of first integrating over G2 and then of D4, you can first integrate over D4 and then G2. Okay, and so when you first integrate over D4, this compact group of type D4, you get the following integral. And it turns out, and so because I have these two D4s, split D4 and compact D4 inside of E8, if I integrate over the compact D4, I get a function on the split D4. Okay, and when you do this, there's a Siegel-Vey theorem that comes into play. So if you do this integral over compact D4, you get a function on split D4, which I've called theta of 1. And one can prove an identity between this theta of 1, this integral here, and an Eisenstein series on split D4. So this is a Siegel-Vey theorem. It says that the theta lift of the constant function is an Eisenstein series on some other group. So finally, and this is sort of the whole point of going down this route, is to, because one can prove the Siegel-Vey theorem, and so and one can finally evaluate the inner product of phi, the cusp from phi, against this Eisenstein series. So recall, I'm trying to prove that this integral is not zero, where I have the cusp from phi and this derivative of the theta function, and suffices to prove that this double integral is not zero. And now we've said that the H integral of the derivative of the theta function is an Eisenstein series. So it suffices to prove that if I take the inner product of phi with this Eisenstein series, I get something non-zero. And finally, this inner product of the cusp form with the Eisenstein series, this Eisenstein series is on split D4. It's not on G2, it's on split D4, and I pull it back to G2. This integral turns out to be of Rankin-Selberg type. I can identify it with an L function. So here's a theorem of Nadia Gravich and Avner Segal, and then generalized by Avner Segal in a second paper, that it says that this integral of the Eisenstein series with the cusp form represents the partial standard L function of the cusp form evaluated at s equals 3. So this is an automorphic normalization of the L function. And so I'm just gonna finish off on one last slide. So in order to conclude the theorem, I need to know that finally that this integral of the cusp form against the Iceland series is non-zero, and this integral of the cusp form against the Iceland series is basically an L function. So more precisely, what is it? So I said in this theorem 6, it's approximately equal to. So more precisely, one can prove that the integral of the cusp form against the Iceland series is a particular vector valued, a particular vector which I've called I sub m, which depends upon m, which sits inside of UM check times the L function evaluated at s equals 3. So in order to know that this integral on the left is non-zero, I need to know that I sub m is non-zero, and I need to know that the L function is non-zero. And so it turns out that s equals 3 is in the range of absolute convergence for the Euler product defining the L function. So this follows from work of Goran Mueck, who wrote down all of the unitary representations on p-adic G2. So using Mueck's result on which representations of G2 of QP are unitary, you can prove that the partial standard L function at s equals 3 is non-zero. So that takes care of the L function bit. And then finally, you need to prove that I sub m is not zero. And this is just some I sub m, it's just some integral that's happening. It's a purely Archimedean integral. It's an Archimedean zeta integral, a vector valued Archimedean zeta integral. And you need to know that it's non-zero. And the last step is, so it took me, I tried to just compute this Archimedean zeta integral for a bit, and I couldn't evaluate it. So anyone who's worked with Archimedean zeta integrals before knows that, sometimes they seem simple, but sometimes they turn out to be quite complicated to try to evaluate. So it turns out one can do a trick to evaluate the Archimedean zeta integral, or at least to show it's non-zero. So one can construct, for any m at least 2 even, one can construct a cusp form, explicit cusp form phi on G2, such that the integral of the derivative of the theta function against the cusp form is non-zero. So, but this integral is the L function times this Archimedean zeta integral. And so if this is a non-zero, then the Archimedean zeta integral has to be non-zero, and that finally proves the theorem. So hopefully I didn't lose everybody. Thank you for your attention.
Okay, thank you very much for the nice talk.